Alrighty, in this video we're going to be using logs to solve various equations such as this one, but also some problem solving applications later in the video. So let's get started. In this first problem I have 1 plus 2 log 10 of x plus 1 equals log base 10 of 2x plus 1 plus log base 10 of 5x plus 8. So the first thing I notice when looking at a problem like this is that we're solving for x, but also I'm looking at this problem and recognizing that the majority of the information in this question is a log base 10. They're all in log base 10 form, except for the one at the very beginning. So what I'm going to do is I'm going to rewrite the equation and change two things. The first thing on the left hand side here, I'm going to change that 1 into a number that is in log base 10. And in the second part of the left hand side, I'm going to take that 2 and put it in the power of x plus 1. So let's write it out. Ooh, brand new pen. It's a bit hard to get off. Okay, here we go. So 1 I'm going to represent as a log base 10 of 10 to the power of 1. That's what 1 is, because log base 10 of 10 just cancels out and I'm left with this 1. So this is an appropriate representation for the number 1. I'm going to add to it log base 10 of x plus 1 all squared. So that squared term comes from the fact that the 2 used to be out the front here and I've brought it up into the power using one of my log laws. Now I'm apparently saying that that's equal to log base 10 of 2x plus 1, and I'm adding to that, if I have room, which I should, log base 10 of 5x plus 8, which just fits in right there. All right, so two things I've done. I've put this in log base 10, I've put this 2 up here, so now all of my terms throughout this equation are in log base 10, and I need to apply log law, another log law, to kind of combine these terms and get rid of the addition here. So when you are adding logs with the same base, you can multiply the terms. So I'm going to be multiplying 10 with this x plus 1 all squared. So I'm going to have on the left hand side a log base 10 of 10 lots of x plus 1 all squared. That's that log. This log on this side is going to be log base 10 also, but of 2x plus 1 multiplied by 5x plus 8. So just like on the left hand side, on the right hand side I have multiplied these two because I have a log with the same base. My next step in this equation or expression is to recognize that I have a left hand side and a right hand side which are both log base 10. So these log base 10s can just go away, because if these two sides are equal and they're both log base 10, then this expression here must be equal to this expression over here. So I'm going to write that down as my next step. I'm going to say, well, should I expand at the same time? No, I'll save that for now. I'm just going to say 10 lots of x plus 1 squared is equal to 2x plus 1 multiplied by 5x plus 8. So we've changed this equation that was in terms of logs, we've turned it into an equation which is just in terms of x, and it's just a regular old solve now. So I'm going to expand and simplify both sides and see how we go. So on the left hand side, I'm first going to expand x plus 1 all squared and then multiply by 10. So I'm going to have 10 outside of, I'll start here, 10 outside of x squared plus 2x plus 1. That is x plus 1 all squared expanded out like this. That's going to equal, I've lost, my equals are no longer in line, but so be it. I'm going to use FOIL to expand this. 2x times 5x is 10x squared. 2x times 8 is 16x, but I've also got a 5x here, so add them together and you get 21x. And then one lot of 8 is just 8. Now I can expand through, and I'm going to get over on the left hand side 10x squared plus 20x plus 10 equals 10x squared plus 21x plus 8. Okay, I've got a bit of simplifying I can do now. There's a 10x squared on both sides of my equation. So they are going to cancel one another out. So I'm going to have this cancel out with this guy. And on the left, I have 20x plus 10 must be equal to 21x plus 8. So I'm going to subtract 20x from both sides, which will remove this term and reduce that to just x. And I'm going to subtract 8 from both sides also. So 10 minus 8 is going to be 2. And 21x minus 20x is just going to be x. And we end up with the expression x equals 2, or 2 equals x, which is probably not an accurate statement because x is what equals 2. 2 equals 2. So x equals 2, final statement. That's question 1 done. Alrighty, question 2 today in this video says, the number of bacteria N in a culture increases exponentially with time according to the rule N equals A times B to the T. So I'm going to write that down here. N equals A times B to the power of T, where T is time measured in hours. When observation started, there were 1,000 bacteria, and 5 hours later, there were 10,000 bacteria. Find the values of A and B. Well, first things first. When T equals 0, so that's initially, it said we had 1,000 bacteria. So this capital N is 1,000. I'm going to use that condition here. And I'm going to say, well, therefore, 1,000 must be equal to A times B to the power of 0. But the power of 0, anything to the power of 0 is 1. So we really just have A times 1, which is just A. So A must be 1,000. And hence, I'm going to update my equation here and say, therefore, N must be equal to 1,000 B to the power of T. That's the first step there. We have a second bit of information though. It says 5 hours later, or when T equals 5, the population of bacteria was 10,000. So I'm going to say when T here equals 5, N equals 10,000. And therefore, we're going to substitute into this new expression, not the original expression. And we're going to get 10,000 equals 1,000 B to the power of 5. Divide both sides by 1,000. And I get B to the 5th equals 10. And I can either take the 5th root of 10 here or raise it to a 5th. I'm going to raise it to a 5th, and you'll see why shortly. So B is therefore 10 to the power of 1/5. And when I substitute that back into this equation, I'm going to therefore get N equals 1,000 times 10 to the power of a 5th to the power of T. And the reason I've left it as a 5th is because if we have a power being raised to another power, we can multiply those terms together and hence simplify this finally for part A to N equals 1,000 times 10 to the power of T on 5. T times a 5th is just T on 5. And this is, I think, my best expression for my population. Right, so we've cleared that off. We've got our expression up here now. We've solved for A and B. And now part B says, find to the nearest minute when there were 5,000 bacteria. Now before we start, let's keep in mind that T is in terms of hours. So if we get a decimal here, like a really small decimal, like 0.08 or something, that's not necessarily a bad thing because that's in terms of hours and we just need to convert it to minutes. But let's move on. So it wants when there were 5,000 bacteria. So if you're ever looking for a when, it's probably your T variable. So I'm going to say when N equals 5,000, which is the situation we're trying to solve. I'm going to substitute 5,000 in, and I'm going to get 5,000 equals 1,000 times 10 to the T on 5. This one is a straightforward division of 1,000, so I'm going to get 10 to the power of T on 5 is equal to 5,000 divided by 1,000, which is just 5. Now, unfortunately, I can't just divide by 10 here because this 10 has some stuff going on in its exponent, and hence we can't just divide by 10. But what we can do is take the log of base 10 on both sides, which will cancel out this guy. So on this, I'm going to, maybe in green, I'm going to do log of base 10 on both sides of this equation. Okay, so my next line, this log base 10 and 10 are going to cancel out completely, and I'm going to be left with t on 5. I'm wary of the fact I'm close to running out of room. T on 5 is going to be equal to log base 10 of 5. Okay, we're getting somewhere, and finally, I'm going to multiply through by 5 and get the expression t equals 5 log base 10 of 5. All right, great. And this is where the extent of my knowledge runs out. And I, of course, have to use my calculator, which I'm going to bring up now. Okay, and we're looking at trying to substitute in 5 log base 10 of 5. Now, handy on these graphics calculators, you can put in log whatever base you want. On the regular scientific calculators, fortunately, it is in log base 10, so we don't have to worry about it. But I'm going to write in 5 times log, which is down here. I need to go control log of base 10 of 5, and the answer is going to be, if I do approximately equals, because I'm in exact value mode, 3.4948, right? That's very close to 3.5. I'm just going to take the answer minus 3 to get just the decimal. Let's go with the approximate decimal here. Whoa, let's go back. Let's go up. Bit of calculator usage here. This answer minus 3, and I'll get the approximate answer in decimal form, and I'm going to now take my answer and multiply it by 60 to get the number of minutes. I'm anticipating pretty much getting 30. Oh, I've done it again. Let's take this answer and approximate it. 29.691, and that's my minutes. I have to remember to also include in my 3 hours. So I have 3 hours and 29.69 minutes, which I am going to go ahead and say t, the number of minutes after the experiment started. 3 hours in minutes is 180 minutes, plus that, let's just say 30. I'm going to say it's approximately 210 minutes. Right, I decided as well just to pop up the answers from part A and B because we have kept rubbing them out. So A was 1,000, B was 10 to the 5th, or the 5th root of 10, and T for part B was approximately 210 minutes. Part C gets a little bit more tricky now because it's actually asking for an inequality. It's asking us, find to the nearest minute again when the number of bacteria first exceeds 1 million. So we're going to say, when does 1,000 times 10 to the t on 5, when is that greater than 1 million? We're going to put a t value in there, and at some point it's going to be greater than 1 million, and we're just going to solve this inequality here. So again, I'm going to start by dividing by 1,000 on both sides. So I'm going to get 10 to the power of t on 5, just like before, must be greater than 1 million divided by 1,000, which is just 1,000. Again, I'm going to take log base 10 of both sides. This time I might be able to do this without a calculator. I'm going to get, if I do log base 10 on this side, I'm just left with t on 5 again. And that has to be greater than log base 10 of 1,000. But here's the thing, 1,000 is just 10 cubed, right? So I'm going to write in here 10 to the power of 3, if that's okay. Log base 10 of 1,000 is log base 10 of 10 to the 3. And so this right-hand side, t over 5, this right-hand side is going to be, log base 10 of 10 is going to cancel, and I just get 3. Now if I multiply across by 5, I'm going to get t must be greater than 15. But keep in mind, my 15 here is in hours. So I need to multiply by 60 to get my time in minutes. So 10 times 60 is 600, and half of that's going to be 300. Add them together, and t is going to be, needs to be greater, not equal to, but greater than 900 minutes. After 900 minutes passed, the bacteria will be at least 1 million in size. Okay, and finally, the last question says, how many bacteria would there be 12 hours after the first observation? Now remember, there were 1,000 bacteria after the initial first observation. So in the time that passes, then we're trying to solve for when t, or what value for t equals 12 would be n. So this time we're actually solving for n. So we're going to say when, this time, t equals 12. So when t equals 12 hours, we're going to say n is going to be equal to 1,000 times by 10 to the power of 12 on 5. Okay, now this is a simple plug and play in your calculator. You actually don't have to do any log laws here. So I'm going to grab my calculator out again and let's see. So 10 to the power of 12 over 5 times 1,000. 1,000 times 10 to the power. Now I'm going to put in a fraction here, control divide to get a fraction, and it's going to be 12 over 5, which of course is going to be 2.4, I believe. Anyway, 12 over 5, and I'm going to go control equals for an approximation, 251,189, exactly 251,189. So n after 12 hours will be 251,189 bacteria in the population after 12 hours. Now, keep in mind the previous example, just to verify a little bit here, make sure we've made no mistakes. In the previous example, we had after 15 hours, 1 million bacteria. This time after 12 hours, 250,000. That seems about appropriate, especially because after 3 hours or 3.5 hours, we had 5,000, was it 5,000? What was it? Yeah, 5,000 bacteria. So I think all the times and the number of bacteria makes sense. Hope this problem solving and the previous log equation of solving helped a little bit. If you have any questions or any specific problems that you want help solving, make sure you post in the comments or send me an email if you're one of my students.